All right, we're back. This is page 6, kind of like part 2 of note 17. And we're talking about just calculus stuff, so let's keep going. So to remind you, we've already done this part of the problem. So we know that g of x is the integral from 4 to x of f of t dt. We're given the graph of f. We already figured out these parts, and now what we want to do is determine the x-coordinates of the points of inflection of g of x. So since we're given the graph of f, I would like to base my explanation on the graph of f. So let's see how we can do that. Well, we know from the prior video, which I'm assuming you watched, that g prime of x is f of x. That's a second fundamental theorem thing. It's really f of x times 1. We're not writing the 1. So this is the case. And now what I like to do is I like to look for relative extrema. That is my favorite way of identifying the points of inflection of a function. Look for the relative extrema of the function's derivative. So the relative extrema of the first derivative. So in this case, this is actually the graph of the first derivative. So everywhere this has a relative minimum, like here and here, or a relative maximum, like there, that's a place where the second derivative, since the derivative, the first derivative is changing from decreasing to increasing, and then increasing to decreasing, and then decreasing to increasing. That means the second derivative is changing sign, right? So the second derivative goes from negative to positive at the first point that I indicated. So at this point, that's where the second derivative goes negative to positive. At the second point that I indicated, the second derivative goes from positive to negative because the slope of the derivative goes from positive to negative, right? The slope of the derivative is the second derivative. And then at this third point, the second derivative is changing from negative to positive. I don't want to get into the second derivative part. So what I'm going to do is I'm going to say negative 2, 2, and 6. So this is true. So I'm going to say that g of x has point of inflection at x equals negative 2, x equals 2, and x equals 6. So I'm going to do all three at once because I abbreviate that so often that I forgot how to spell because there for a second. Because g prime of x, which equals f of x, has relative extrema. Has relative extrema at those values. That's all you need. That's an acceptable justification for points of inflection. Every time the first derivative has a relative extrema, either maximum or minimum, the original function is going to have a point of inflection. That's my favorite way of justifying it. I recommend it. The only time you ever like run into trouble with that is if the derivative is not continuous and has like a jump discontinuity at which you change from the derivative change increasing and decreasing. It didn't happen here. When we get to that at some point, I'll point it out, or maybe we already got to that because these notes are way past points of inflection and things like that. So hopefully you're aware of that. If there's a relative extrema on the first derivative, then there's a point of inflection. That's not the only way to get a point of inflection. You could also have, so I guess I am going to get into it. You could also have like your derivative could look kind of like, I don't know, maybe like this, right? By definition, there's no relative extrema there, but if this is f prime, then f prime does change from increasing to decreasing, which means there is a change in the second derivative sign, which means there is a point of inflection. So that's a little trickier though. And I pretty much use this relative extrema thing like 100% of the time, if I can. Every time I can use it, I'm going to use it. All right, intervals on which g of x is decreasing in concave up. So I'm just going to repeat that g prime of x is f of x. So g of x is increasing concave up. Okay, so when does that happen? Well, increasing is when the first derivative is positive. Concave up is when the second derivative is positive. But I want to base everything on the graph of f of x because that's what I have. So instead of saying that the second derivative is positive, I will say that the first derivative is increasing. So I'm going to say g of x is increasing concave up when g prime of x, which equals f of x, is positive and increasing. Okay, so now let's find where Oh, sorry, decreasing. So decreasing, we need f prime to be negative. So when f prime is negative, okay, so if g of x is decreasing, it means f prime is negative. If g of x is concave up, it means that f prime is increasing. So we need negative increasing. Let's take a look at our graph. Where is it that our function is negative but increasing? So negative and increasing. Looks like negative 2 to 0, and then negative and increasing from 6 to 7. So negative 2 to 0 and 6 to 7. Therefore, when x is an element of negative 2 to 0 and x is an element of 6 to 7. So those are my answers. So I've given a justification, right? The derivative g prime is negative, which means the function is decreasing. G prime is increasing, which means the second derivative is positive, which means that the function is concave up. So we covered it and we have an explanation. That's what we're looking for. That's awesome. All right, what about range? Well, so the range of a function on a closed interval is really just if we could find the absolute minimum, the absolute maximum, the range will be everything in between, assuming that the function is continuous. This function is continuous because this function is differentiable, right? The derivative of g is f of x. F of x exists everywhere from negative 4 to 4, which means that since the derivative exists, the function g of x is differentiable. So if differentiable, then continuous. So I'm going to say g of x is differentiable, which implies continuous. Therefore, absolute max and min are at an endpoint or critical point. So this is going to be the candidates test. This actually, I love this question. My favorite way to justify a point of inflection is to use the relative extrema of the graph of the derivative. My favorite thing to do might actually be to use the candidates test. I love it because you don't have to like figure out, is it a relative max, relative min? Just find the y value and move on. So an endpoint or a critical point. Okay, so the critical points are when g prime of x equals f of x equals 0. So that's going to be at x equals, I hope they're good. I don't want to do a lot of, basically I just don't want to do algebra 1 stuff. All right, so zeros here, 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 here. That's a lot. Negative 3, 0, 4, and 7. Also, that looks like the same color that I used before. What other color options? Let's expand our palette a little bit. Here, 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 here. Negative 3, 0, 4, and 7. That's a lot. All right. X equals negative 3. X equals negative 3, 0, 4, 7. 0. X equals 4. I always have this open on my other monitor, at my other display. Sorry, I'm like an old person. I say monitor. But then I always forget to look at it. It's why I scroll back and forth so much. I don't know. Maybe that helps you also keep up. So now what we're going to do is we're going to make a table of like 1,000 values, unfortunately. So x, g of x. So the endpoints are negative 4 and I thought it was negative 4 to 4. Negative 4 to 8. Ugh. All right. I think I'm thinking of the previous problem. So it's going to be negative 4, negative 3, 0, 4, 7, and 8. Good grief. 4, 7, and 8. All right, now we got to find these values. So keep in mind that g of x is actually the integral from 4 to x. So g of negative 4 is going to be, I'm just going to write this directly, right? So I change the bounds and I flip the sign, swap the bounds, flip the sign, f of t dt. So can I find that? Let's see. So this and this will cancel. And then this is negative 1. And then what is this full thing here? So this, well, this is 3. So that's negative 1. I'll write it out. It's the negative of -1 plus 3 plus 3. So I think it's 5. Well, -5. I think that's -5. Okay, I think that that's what you get at -4. I think it's -5. All right, what's next? I need to now find g of -3. So that's going to be, again, flip the bounds, change the sign, -3 to 4 of f of t dt. So that's going to be the negative of, what do we got here? So I think I can just subtract another 1/2 because we're picking up, what are we doing? How am I, there's too much going on here. I'm picking up this part and add another -1/2. So that's -1/2. So it's -1.5 and then 6. So positive 4.5. But because it's the opposite, so that's -4.5. All right, now I think they're going to get easier because as you get closer, it should. 0. So g of 0 is the negative, again, 0 to 4 of f of t dt. That is definitely -6, right? The negative of 6 because the integral is 6. So -6, I don't know. It's good for you. I mean, it really is. G of 4 is the integral from 4 to 4 of it doesn't matter what, because that's going to give me 0. So that's awesome. So 0. Now I got to find 7. Then I got to find 8. All right, so for 7, I'm looking at this whole region. What color to use? I'm going to use this color. Looking at this whole region here, right? It's a triangle. Oh my God. It's a triangle that has a base of 3 and a height of -2. So it's going to be 1/2, 3, -2. So -3. So g of 7 is the integral from 4 to 7 of f of t dt. And we found that that was -3. So far, so okay, I guess. -3, and then 8. Well, all right, so at 7, we're already at -3, and then we're just going to add whatever we get here, which is half of a rectangle that has an area of 2, so it's just 1, or 1/2 base times height. So we're at -3, and we add 1, we're at -2. So this is -2, and what I did there was I basically did, I did -3 plus the integral from 7 to 8 of f of t dt. Okay, so therefore, the absolute minimum is, so this is the y value, is -6, and the absolute maximum, which is again the y value, is actually 0. This thing never gets above 0, is 0. So the range is -6 less than or equal to y less than or equal to 0. Candidates test. It's really useful. So I guess I should say that I'm going to put it up here by candidates test. Right, give it its due by candidates test, period. Critical points, absolute min, absolute max, you make your table. Really common thing to do. I mean, this is a lot of points. You don't usually do it for this many points. All right, let's do this last problem and see how it goes. So we want to find the second derivative, so that's great. So first we have to find the first derivative, dy dx. All right, dy dx. We're finding, here's our integrand. We're going to sub into that the upper bound. So it's going to be the upper x squared sine of x squared squared, so x to the 4th, times the derivative of x squared by the chain rule, 2x. So this will be 2x cubed sine of x to the 4th. 2x cubed sine of x to the 4th. That's the first derivative. Second derivative is a product rule. So it's first derivative of the second. The derivative of sine of something is cosine of that thing times the derivative of that thing. So 4x cubed plus second, which is sine of x to the 4th, times derivative of the first, which will be 6x squared. Yikes. So we get 8x to the 6th, and then cosine of x to the 4th, plus 6x squared. That seems like so few x's, but I think it's right. Sine of x to the 4th. Yeah, there we go. What can we factor? We can take a 2x to the 2x squared out. I don't really know that this is particularly useful. Will leave us with 4x to the 4th cosine of x to the 4th plus a 3 and then sine of x to the 4th. Oh my gosh. I think that's it. All right, tons of math done in this, a lot of calculus. So we got to use my favorite point of inflection justification. We got to use candidates test, which I really do love using. We got to geometrically find a lot of areas, things like that. And then a straight second fundamental theorem followed by a product rule with a lot of chain rule stuff. So that's the end of this. I will be back in another video, probably working on the next set of notes. I don't know what my plan is right now. So hopefully I'll see you in the next one. And I really hope you are finding these helpful.